Hello all my physics students. Welcome to this video tutorial on how to use geometry and trigonometric ratios to solve physics problems. Up here I have a very strange looking word, SOHCAHTOA, not to be confused with Krakatoa, a very large and dangerous volcano. SOHCAHTOA is a mnemonic device that we're going to be looking at later in this lesson that will allow you to remember the trigonometric ratios, to use the power of triangles to solve physics dilemmas. Vectors have magnitude and direction. Vectors are drawn in the shape of an arrow that is pointing in the direction and is drawn to scale for the magnitude. In this particular case, we have vector A and vector B that are being added, and then the resultant is found down here. The resultant is what we get when we add or subtract our vectors. We're going to use geometry to find that resultant and to find the direction of the resultant. It all began a long time ago with Pythagoras and his theorem. Pythagoras was an ancient Greek mathematician, and he found that the squares of sides of a triangle, if you take the square of each of the sides of a triangle, you'll get the square of the hypotenuse of the triangle. Now this can be very useful for finding our resultant when we're looking at vectors that make right angles. Robert walks 300 meters east. In physics, we generally show that east is to the right, west is to the left, north is up, south is down. So we're going to draw this vector, labeling its magnitude, vector showing its direction. So he's walking 300 meters to the east, and he turns around and he heads 180 meters to the south. And we want to know, what is Robert's displacement? In other words, how far is he from where he started from? Displacement has a magnitude and a direction. So right now, let's just find the magnitude of his displacement. We're going to do that by using the Pythagorean Theorem. A squared plus b squared equals c squared. So we're going to do 300. It doesn't matter which side you choose for each, plus 180 squared, and that's going to give us c squared. Well, when we put that in our calculator here, we get this incredibly large number that c squared is equal to 122,400. Don't forget to take the square root of that, because we don't want c squared, we want c. And that's going to be the square root of this number. And when we do that, we get a magnitude for Robert's displacement of 249.857, and it keeps going. Thinking about our significant figures, now I should have put a decimal here to make sure. Let's just say we have 3 significant figures here. I'm going to round this to 3 significant figures. It means I'm going to look at the fourth one. It's an 8. I'm going to round this one up. But when I do that, I end up with 350. So we're going to say that's 350 meters. That is Robert's displacement, or the magnitude of his displacement. We still haven't solved exactly the direction that it is. We do know that it's southeast of where he started from. This brings us to SOHCAHTOA. So stands for sine equals the opposite over the hypotenuse. So cosine is the adjacent over the hypotenuse. So ca, and then tangent is the opposite over the adjacent. So if you remember this SOHCAHTOA word, you'll always remember the ratios of these different sides. Well, what's an opposite? What's an adjacent? We know that a hypotenuse is the longest side of a triangle. We know that from doing the Pythagorean theorem. But the adjacent and the opposite might be new to you. We call an angle that we're looking for theta, and in this case, this is where our angle theta is. This is the 90-degree angle in this right triangle. The opposite side is the one appropriately that's opposite of the angle you're looking for, and the adjacent makes up part of the angle. Let's look at an example. An airplane is flying due north at a velocity of 100 meters per second. So here he goes, he's 100 meters per second. But there's a wind blowing to the east at 20 meters per second. What's the resultant velocity of the plane? Well, we can find the resultant here by using the Pythagorean theorem. 100 squared plus 20 squared equals our c squared. So let's put that in. 100 squared plus 20 squared gives us c squared is equal to 10,400. Let's take the square root of that. And when we round this, we get 101 meters per second. So the plane is actually flying a little bit faster than it should be because it's being carried slightly by the wind. But in what direction? If this pilot is heading somewhere and he's trying to fly due north, he's not going to get there. He's going to be blown off course. But by how much of an angle does he have to compensate for that wind? That's this angle theta here. Let's use our trigonometric ratios to help us find this angle. I don't want to use the number that I calculated because it's not going to be as accurate. So let's find one that we can use that allows us to use this side and this side. This one is our adjacent and this one is our opposite. So if I have opposite and adjacent, I'm going to use the tangent. Here's a close-up of a TI-84 calculator. You may have something similar or you may not, but here's the tangent key on this calculator, and above it you'll notice a blue thing that says tan -1. That's the inverse tangent. We're going to be using that to solve this problem. Well, tangent of theta is going to be equal to my opposite, which is 20, over my adjacent, which is 100. Let's find out what that is. What's 20 divided by 100? Well, that's going to be 0.2. That's an easy one. Okay? So the way these ratios work is these very clever Greek guys realize that certain ratios in triangles correspond to the number of degrees in that angle, and they made enormous charts that you could look at and find the degrees of your angle. Well, your calculator or your computer is programmed to give you those things. So if we tell it the ratio and the right trigonometric formula here, then it's going to tell us what that degrees of angle is in that triangle. So what tangent is going to be equal to 0.2? So the way that we do that is we're going to use this function right here. Okay, you do, on my calculator you hit second, then you hit tangent, and then you do 0.2, and it's going to tell me that the value of theta is 11.3 degrees. Okay, now I can look at my drawing and say that's 11.3 degrees to the east of north. Okay, tells me exactly what direction. So this pilot, if he wants to fly due north, is going to have to compensate for this wind 11.3 degrees. What if we only know the angle and we know the adjacent and we're trying to find the opposite? I know the number of degrees in theta. I know my adjacent. And my opposite, in this case the height of the tree, is what I'm trying to find. Okay, so that is my question mark. Well, I still have opposite and adjacent and theta, so I'm still going to use tangent here. And the tangent of theta is equal to the opposite over the adjacent, TOA. Okay, so, but this time the tangent of theta is something that I know. So we're going to have to rearrange this formula to solve for the opposite. So I'm going to multiply both sides by adjacent. Little algebra here. Okay, so the opposite is going to be equal to the adjacent times the tangent of theta. Okay, so let's try this out. If the opposite is equal to the adjacent, then that is going to be my adjacent 76 meters times whatever the tangent of theta is, tangent of 32. So I'm going to put in my calculator 76 times tangent 32. Make sure that your calculator is set to degrees and not to radians. If you're not getting the answers I'm getting, that might be your problem. 76 times, and then I hit tangent 32. And I get a height of this tree that is 47, rounds to 47.5 meters.